Without any further ado, one and all, please allow me to once again invite Peter Jennings to the lectern to introduce and to moderate our next keynote speaker. Peter.
Well, colleagues, it gives me great pleasure to introduce Michelle Simmons. Michelle is the Director of the Centre of Excellence for Quantum Computation and Communications Technology at the University of New South Wales. And she is an Australian Research Council Laureate Fellow. Michelle has pioneered unique technologies internationally to build electronic devices in silicon at the atomic scale, including the world's smallest transistor, the narrowest conducting wires, 3D atomic electronics, and the first 2-qubit gate using atom-based qubits in silicon. As founder of Silicon Quantum Computing Proprietary Limited, her team is at the forefront of developing a silicon-based quantum computer. The atomic electronics research led by Professor Michelle Simmons has the ultimate goal of developing a scalable phosphorus in silicon quantum processor. Professor Simmons' group leads the field internationally in making precision atomic electronic devices in silicon for both conventional and quantum computing. And this has led to the development of the narrowest conducting wires in silicon, the development of the smallest precision transistors, and the first 2-qubit gate between atom qubits in silicon and more complex architectures towards error correction. I should at this point share with you that I'm actually a graduate in medieval history. So Michelle, it will take you to explain to the audience exactly what I've said. So Michelle is one of a handful of researchers in Australia to have twice received an Australian Research Council Federation Fellowship, and she has now received a Laureate Fellowship. She's a Fellow of the Royal Society of London, the American Academy of Arts and Science, the American Association for the Advancement of Science, the UK Institute of Physics, the Australian Academy of Technology and Engineering, and the Australian Academy of Science. In 2018, Michelle was named Australian of the Year. It goes without saying, one of the nation's preeminent awards. Michelle, it's a delight to have you with us to talk to us about AUKUS technology potentials. Ladies and gentlemen, please welcome Michelle.
Thank you very much, Peter, and good morning, ladies and gentlemen. I am Australian. I moved to this country over 20 years ago and became a citizen soon afterwards. But I was born British, I grew up in the UK, and I have close family in the US, with roughly 60 visits to the US over the last 20 years. So consequently, a part of me has always felt a little AUKUS, even before that invention of the term. Our three countries have many things in common. We have, as we heard this morning, shared values of freedom and democracy, shared ideals about fairness and respect for others, and shared interests, both economic and strategic. And of course, we have a shared language. But we also have our differences. Over the years, I've been fortunate enough to work with scientists from all over the globe. Many talented people from the US and from the UK have come to join my team, and several members of my team have gone and taken up positions overseas in the US and the UK. Along the way, I've been rather surprised about how well we live up to our cliches. The Americans are really second to none in competitiveness, in the pursuit of results, and in innovating at scale. The British offer nuance, intellectual firepower, and do fundamentals very well. While we Aussies, we have a unique pragmatism and an openness and willingness to give things a go. And that's the reason why I moved to this country. Today I'm going to talk to you about quantum computing and the potential role that AUKUS can have in this area. And if there's one message that I do want to get across, it's that our differences are just as important as what unites us. For if AUKUS makes sense in light of our common goals and our determination to share challenges together. It will only prove effective because of the different strengths that each of us brings to the partnership. Today, quantum computing is recognized globally as a transformational technology. Put simply, it allows one to solve problems in real time that otherwise would take classical computers thousands of years. This extraordinary prospect arises from our ability to manipulate the world at the smallest length scales, either individual photons of light or individual atoms, which in turn opens up the possibility of using quantum states rather than classical states for computing. And that provides an exponential speed up in computational power for certain types of very high-value problems. Once realized, such a capability will affect nearly every industry that's dependent on data. And examples of potential use cases include accelerating the vast majority of today's machine learning and AI applications, improving the energy density of batteries, which is key to our translation to renewable energy, developing catalysts for the production of low CO2 fertilizers, solving intractable problems in portfolio and network optimization, and which is particularly important for AUKUS, deployment in defense applications such as code breaking. As you might imagine, the value of such a capability would be incredibly high. The consulting firm McKinsey has estimated that the annual global revenues from quantum technologies will reach as high as 100 billion. BCG has forecast quantum computing revenues alone will be between the US 90 and 170 billion. And our own CSRO has made very similar forecasts, identifying quantum computing as a particular area of advantage for Australia. By 2040 in particular, having roughly 3 times the projected market size of quantum sensing or quantum communications, which are 2 other technologies that we have here in Australia and globally. The real value, though, is not to be found in the direct revenues of the quantum computing producers, but in the benefits to the end users. Here again, BCG has estimated that end users could see US $450 billion to $850 billion in annual revenue, arising from the improvements to operations, creation of new services, and provision of higher quality outcomes that will flow from quantum computing applications. McKinsey has also estimated quantum technologies could create $700 billion US across industries. The rewards then are substantial, and the challenge is for us getting to them. One of the key differences that occurs in the quantum computing field compared to classical computing is the large variety of different physical platforms that you can use to build a quantum computer. Indeed, there are arguably 7 different materials, systems that you can use, from silicon to superconducting to new states of matter not yet realized called Majorana fermions. Some of the original materials were superconducting qubits, made of loops of superconducting material on top of silicon to create magnetic fluxes used to store information and process information. And this technology is the technology that's being pursued by Google, IBM, Rigetti, and others. Another system that was early out of the gates was ion trap processors, using quantum states of ions trapped in a vacuum using lasers. And amongst other are photonic systems which use photons of light and defect states in solids. In Australia, we have focused on atom qubits in silicon and optical qubits. One of the significant factors for Australia in our early success is that we got into the field early. The Australian Research Council has a wonderful scheme called the Centre of Excellence Scheme, which in essence started back in 2000. Back in 1999, I came to Australia and we formed the first Centre of Excellence in Quantum Computing Technology with 50 researchers working across Australia to form a national effort to try and build a quantum computer in silicon and in optical systems. To set up such a team in such a technologically challenging area is not trivial and it's expensive. Yet we've now been successful in running 2 further Centres of Excellence, each having funding for 7 years, giving a total of 25 years of sustained funding. The Centre produces more than 100 papers per year for over 20 years, with over 2,250 papers in quantum information science, primarily in quantum computing. And importantly, over the last decade, the Australian Research Council Centre of Excellence for Quantum Computing has produced between 12 and 15 papers in the papers in Natures and Science, every year, which is more than 1 per month. And this is the highest that I've seen of anywhere globally. With UNSW Sydney as the headquarters, we now have 7 universities in Australia, 25 international partners in the centre with over 250 staff and 130 PhD students, many of them from overseas. And we've graduated over 220 students since the beginning, and importantly, we've had over 200 granted patents in the field. We've also pioneered the ability to manufacture circuits in silicon with atomic precision and have become the clear global leaders in this technology. So Australia got in early and established global leadership in a key implementation, but others have not been slacked. And having recognised the opportunity, investments by other nations have recently accelerated. In 2017, China has pumped in $10 billion to establish a national laboratory for quantum information science in Hefei. This is one building in one location with 50 professors working under one Uber professor, Zhang Wei-Pan. Their initial strength was in quantum secure communications, having set up a satellite that they put up into the atmosphere called Missyus. And that allowed them to communicate with quantum states absolutely securely. However, they're now actively trying to replicate all the other quantum computing platform technologies, from optical through to superconducting and silicon. And they have a clear stated ambition to beat the US within the decade. In the US, they've taken this field very seriously since the beginning. The Americans have well-established teams in superconducting technology with big global corporates wading in like IBM and Google and Rigetti. Microsoft has come in Majoranas, and there's IonQ and IonTrap technology. These teams have scaled their technologies and are putting their systems online. But their competitive model and their premature role that's been taken on by the software companies may actually be getting in the way of their success. The technology very much demands engineering and fundamental physics. It needs strong academic and industrial partnerships and a hardware mindset. Evidence of this challenge of having that hardware mindset was recently established by Google. Their lead hardware engineer, John Martinez, left the company in 2019, shortly after demonstrating quantum supremacy for the first time, to come and join us. And he described that the cultural divide between software and hardware and between academia and corporate was just too large. The other thing that's happening in the US is they're building 5 large Department of Energy centers, linking universities to industry. And the whole US system has great support from the White House and from other agencies such as DARPA, IARPA, the US Army, Navy, Air Force, and National Science Foundation. Comparatively, the UK came in a little bit later, making its mark in 2014 with the establishment of 4 quantum hubs: the Quantum Computing Hub at Oxford University, the Quantum Communications at York, Quantum Sensing and Timing at the University of Birmingham, and the Enhanced Imaging at the University of Glasgow. And they've spent over £100 million over the past decade. The UK has also recently announced the National Quantum Computing Centre at Oxford, due to open in 2023, with £93 million investment over 5 years. And their goal is to build a 100-qubit NISQ machine. And NISQ stands for Near Intermediate Scale Quantum Machine. So this is a 100-qubit system that they're trying to make. But interestingly, every country now has a quantum strategy, with large-scale initiatives planned. Recent investments over the last couple of years include Russia with $790 million, Israel $360 million, the EU $1.18 billion, Germany $2.24 billion, India $1 billion, and so on. Each country is choosing to focus where they have strengths, but in most instances there is a lot of catching up to do. In terms of publications and impact to date, the countries that lead is the US by far, then the UK, Germany, Canada, and Australia, with Australia leading in silicon quantum computing. In terms of impact, China has a lot more publications, but they're not so well cited. But as I note, their intention is to change this situation rapidly. So what is our status now? In Australia, we have an astonishing 6 centres of excellence where quantum physics is at the core. The largest and longest running is the Centre of Excellence for Quantum Computation and Communication, headquartered at UNSW Sydney. We spun out AUKUS with the junior staff who went to the University of Queensland looking at engineering quantum systems. We have the Centre for Gravitational Wave Astronomy at Swinburne. And then there's the Centre for Exton Science, the Centre for Future Low Energy Electronics, and the recently announced Centre for Quantum Biotechnology. We also have a new network in Software Alliance. There's the Sydney Quantum Academy for education and training. the Australian Quantum Alliance, bringing together all the startup companies through the Tech Council of Australia. And these groups, amongst others, are helping to frame our national quantum strategy, led by the Chief Scientist, Cathy Foley, herself a quantum sensing expert. Equally important, however, is what's happening on the commercial front. And in this respect, I'd like to share some of the observations about the company I work in, which spun out of UNSW and now employs 50 engineers and physicists in Sydney, called Silicon Quantum Computing. Over the past 20 years, at the Centre of Excellence at UNSW, we've pioneered the ability to manufacture circuits in silicon with atomic precision. As I mentioned earlier, we are the global leaders in this technology. Significantly, for quantum computing, our implementation has achieved the highest metrics of any qubit system in the solid state and has key advantages due to its long-term manufacturability. Indeed, our manufacturing capability has a precision that extends beyond the traditional semiconductor foundries. And that's what enabled us in July this year to produce the first integrated circuit made with atomic precision. And not only make that circuit, but to use it to simulate conductance through a small molecule polyacetylene. The company has 5 shareholders, including the Commonwealth Government, one of Australia's largest banks, the Commonwealth Bank of Australia, a national telecommunications company, Telstra, the largest engineering department in Australia at UNSW Sydney, and the New South Wales State Government. And we have a roadmap to build a full-stack processor that could be manufactured here in Australia using atom qubits in silicon. We believe that this is an area for Australia where we can both lead in research and in manufacturing. We already work very closely with our US colleagues, but a critical challenge for us will be to maintain the Australian ownership and involvement as we scale, which brings me back to AUKUS. Given the model pursued by China, I believe it's imperative that we play to our strengths and work together. This is a race, there's no doubt. No one knows who's going to win, but by working together and exploiting our different strengths, we can maximize the odds that one of us will win. So what would this mean in principle? Here are my thoughts. Every country should invest and play to its own strengths. By having a strong alliance with the AUKUS partners, we can avoid duplicating efforts and work together. This requires trust, which is complicated when you work with competitors or compete with collaborators. But it's up for each country to lead in the area, to put its weight behind where it leads. If we make the rule that every leading technology is advanced from others, from the knowledge of others, we can learn from one another. For having John Martinez come from Google here, he showed us the importance of how to integrate software into the hardware as you build. And we shared with him the knowledge of silicon material systems and semiconductors that he needed to get the quality of the superconducting qubits up. But it's also important that we treat each other with respect and as equals. If we don't do it, it's conceivable that the big guys in the room, that's the Americans, end up with everything. And above all, it's essential that we maintain our own locally based strengths in our own countries. This will provide a larger talent pool to the whole alliance. It will spread the risks in pursuing difficult technological challenges. But perhaps most important of all, it will continue to provide us with that great diversity of thinking and culture that I alluded to right at the outset. I'm not sure that we could have done what we've done with silicon quantum computing and atomic manufacturing here in Australia, anywhere else in the world, which is a testament to the culture and the circumstances I find in Australia. Our alliance becomes stronger when each of us can benefit from the different attributes, skills, and approaches that the others bring. There are several simple ideas that I think can be implemented to put these concepts into effect. For example, at UNSW, we've had a very strong ongoing relationship with the US military since 1999. We've been funded over $36 million from the US Army Research Office in our quantum computing silicon efforts. It would be good to ramp this up now and ensure that Australian defence matches this funding one for one. An even more strategic play would be to take the leading public research teams in every country across the different platforms and make the rule that every country in those platforms shares its knowledge, both to learn from different implementations and to constantly evaluate which technology can win. The US has leadership in superconducting, ion traps and cold atoms. The UK has leadership in ion traps and photonics, and Australia has leadership in silicon and photonics. Another area that I think could be interesting is to create an international centre of excellence for the leading platforms from each country funded by every government. This would send a big signal globally And certainly over my career, I found that the best way to be at the very forefront of the field is to work with the very best across the world, not to limit yourself to one country, but to find out where the best are. And certainly the US, Australia, and the UK would form a formidable alliance in that respect. So whatever ideas are chosen, whether these or others, the principle should still stand, that we play to our strengths, that we each pull our own weight, and that we nurture locally based capabilities. This works for quantum computing because in quantum physics in all three countries, we have something significant and value to contribute. Thank you.
Michelle, thank you so much. And we're going to go to questions from the audience, but let me put a few to you first. Let's start by assuming no knowledge on the part of principally myself in relation to this issue. What is it about quantum computing which gives it the potential to be such a game changer compared to current technology in use?
Yeah, so literally in the classical world, we really only use two states of matters, ones and zero. In the quantum computing world, when you make things very, very small, you can access quantum states, which allows you to use states in between 1 and 0. And quite simply, what that allows you to do is to do calculations in parallel using a quantum computer that you would have to do one after the other using a classical computer. And that really gives you this kind of exponential speed up in computational power. And just to give you a sense, if you were to make a kind of chip now, a silicon chip in your iPhone, it would have roughly 14 billion transistors. And theoretically, it's starting to be proven with the Google result that you would only need a few hundred to 1,000 to outperform quantum bits to outperform that. And so it's really, I guess I don't know how to describe this to you, but it's a technological advancement to be able to engineer things at that scale, much smaller than humankind has done before. But then the power comes pretty quickly. So in the world of quantum computing, it's how many high-quality qubits you can manufacture at scale that will allow you to basically wipe out the kind of calculations you can do with classical computing.
And a qubit, I mean, we talk about a 2-qubit system. Now we're talking about China working on a 100-qubit system. For the uninitiated, a qubit?
A qubit is a quantum bit, and it literally, so in the classical world, a transistor is 1 and 0. A qubit is literally a state that can exist anywhere in between. The way I envisage that is a picture of the world. You sit in the middle, you can point to the North Pole or South Pole. In the quantum world, you can point anywhere on the surface of the sphere, and that is your quantum bit.
And so really the promise is just dramatic speed, but is there more to it than that? I'm trying to understand how to sort of characterise the difference between current and future possibilities.
So it's not just a dramatic increase in speed, because we're used to getting things that are faster generally every year.
Yep.
It's actually being able to do things that we simply can't do. And so, the kind of end point of this is code-breaking, so a 10,000-bit number can be broken. It takes longer than the lifetime of the universe to break the code if you encrypt it with a 10,000-bit number. With a quantum computer, you could do that in an hour. So for data security, that is a massive implication. That's really what kicked off the whole field. But if you look at other things around, so whether it's weather forecasting or drug design, they're things that take lots of time, inaccurate in the case of weather quite often, but in drug designs it takes a decade and billions of dollars to do that, because we simply can't understand all the different interactions of how the drug is formed and how it interacts with the body. A quantum computer, again, will start to make those kind of calculations real time. So it's going to hit a lot of industries.
So in the defence world, I mean, encryption, that's something I understand, or at least I understand the result of that, which is the capacity to hold and keep secrets. But what we're really anticipating in a quantum world, because of the speed of computation that's imagined, would be the ability to decrypt, everything that might previously have been kept secret on a vast scale, as soon as a country has access to a sort of a workable quantum capability. Now, that might be a simple way of putting it, but is that sort of an accurate statement?
That's exactly right. So right. It's a very powerful technology. It is the algorithm that really kicked off US defence getting into this in the first place. Yeah.
So, timeframes. This is a race, as you've said. What's your best judgment, as someone who understands the field as well as you do, about the sort of time frame we're looking at where these capabilities could start to become available?
So definitely within the decade, but I think
Within the decade?
Yeah, what we've been doing with our particular technology is mapping out from the invention of the first transistor to the first integrated circuit in the classical computing world, and then how long before they got products after that. And it's basically, you know, it took a decade to go from a transistor to an integrated circuit, and then about another 5 years before they got commercial products. We're exactly mapping that. So our first transistor was 2012, integrated circuit was 2021, so it's, you know, slightly less than a decade. So within 5 to 6 years, commercial products will come out. And then I guess what you have to realize, though, is it's a computing industry, so it will keep going, you know, for another 70 years, as the classical computing industry has. And the quality of the product is going to keep increasing all the time as you increase the number of quantum bits in the system. So it's a long-term transformational industry that will go on for decades. And I guess the key thing that I've realized is that the people that control the engine, the hardware, ultimately are going to be the people that get all the benefit economically from that technology.
Right. So you sketch a field where, you know, to my uninformed ear, it sounds that Australia has actually had quite remarkable success in terms of its ability to play in this field as a relatively small player. But, you know, in a world where countries are investing billions, what does that say for the state of quantum science in Australia longer term?
Yeah, so look, I think this is, I think, a misunderstanding, because the numbers I mentioned now are countries are coming in, you know, 15 years, 20 years after Australia,
Right,
with the $1 billion. If you look at how much has been invested, even in our Centre of Excellence alone, it's 400 million since the beginning. We then set up a startup company, which is another 83 million. So, you know, we're getting up there already with the investment that we've had to date. So countries are coming in now, but you've got to remember that you have to have the technological skill in areas of deep tech. And I don't know how to describe this to you, but I'm living and breathing this. But you have the hardware, which in itself, you're pushing the forefront of technology that has never existed before. So everything you do is new. But then once you've got the hardware, you have to build the whole, what we call the stack. The control systems on top of that, the high frequency control, the software layers, the interface layers, the algorithm layers, the architecture layers. So there's, you know, every layer of that stack that you have to integrate together to get the product. And so if you come in now and you start from scratch, having not been in that field at all, you've got a whole series of expertises to get to work together, a whole lot of deep tech in every single one of those areas. It is the forefront of what we do, and get that to work. And that is non-trivial. And I think what I've learned is Australia's in a formidable position because we started a long time ago. Having these six centres of excellence, we have thousands of quantum scientists trained across, you know, several different implementations. But Australia's actually in a very good position.
We're kind of at that stage, though, that Australia tends not to be so good at, which is, I guess, the commercialisation, the sort of
Nervous
the
stage.
movement from the idea to the product. And I guess the you know, incentives for people in the field might be to say, well, I can go and work for Apple in the States, or I can go and work for you know, a foreign government potentially paying significant more than I can get in Australia. Are we at risk of actually losing some of this talent, and how do we stop that from happening?
Yeah, so look, again, I hear that a lot. Excuse me, but I actually don't see it. And it goes back to a comment that was made earlier about purpose. When you're at the very forefront of a field and you have a company that's relatively small, then if you join that company, you get to see every aspect of the whole technology come together. So you really feel like you're part of something really big. I know a lot of the big global players, which is why it's a cautionary note, I think, to a lot of the US companies. They hire in, 100 software engineers, and then they find the software engineers don't know how to work with the hardware engineers, and then it fragments. And so actually being small and being fast and being, the cultural ability to work together across different skill sets and with different countries, which Australia is fantastic at, it's actually, I think, a huge competitive advantage where we're sitting.
It's really interesting. Last one from me before we go to the audience, and it goes to your reference to that $37 million investment from the US Army in your research area. What do they know that the Australian Army doesn't know?
Well, I don't know, but honestly, I have found it disturbing, because I think the US they do pride themselves on being at the forefront and picking things up. The fact that they were investing 20 years ago and have continued to invest for that amount of time, they watch very carefully what we do, they know very well. I do think it's time for Australia to step up in that space. Ultimately, the worst thing I think I've seen coming from Britain originally is that we get these technologies to a certain point and then they do tend to go overseas. And it is that kind of doubt, that cultural doubt that we can do things here. But I firmly believe we're in a commanding position in quantum computing where we will have a competitive edge, not in just the technology itself, but in the culture and the way that we've established our businesses. And so, it's ours to lose.
Actually, I do have another question, but it goes to, so I get the point. AUKUS can be a lever to achieve some of the things that you've just been talking about here. Now, you may not want to answer this question, but, I mean, has anyone sort of rung you up and said, hey, we've got an idea about AUKUS that could involve you or involve the quantum sector in Australia? I mean, are these discussions actually happening now?
So look, I think the discussions are definitely happening. I've also heard the call to action earlier on. I think the discussions are happening, but there is still this cautiousness about the security aspect, I think, that makes it very difficult for those nations to get together at the highest levels. I think for me, honestly, my whole career has been based about finding the best, working on the best, no boundaries. Bring people from whichever country, obviously there's some countries not allowed to, but bring people from whatever country to work on to build this technology. I think with this going forwards, if the US, Australia and the UK can get together and really just take the best of each of those countries, forget all the bureaucracy and everything else, just on a technology level, that is what we need to do to be able to secure the future, really, strategically.
Well, ladies and gentlemen, we've really got a tremendous opportunity here to enable you to ask some questions of one of Australia's leading minds on this technology. So I'd like to now hand over to you. First thing I need to do is put my glasses on. I was explaining to Michelle earlier, I need my glasses to see the audience. So I think, do we have one person down this end? We'll go to you first, Leslie. And, well, let's start with you, Leslie, and over to you.
Okay, I think that's working. Okay, thank you very much, Michelle. So Leslie Seebeck, currently at large. That was a really good outline of where we are at, as well as how you see the future going. But I do want to push you on a couple of points. The first is, you've mentioned again that you get the technology to a certain point. How do we actually scale? How do we actually put that production facility in? What's the ecosystem that we require in this country to realise it? The second thing is about just the funding mechanism. At the moment, we have you mentioned the 7 on 7 years sort of funding mechanism. Is that enough for some of these sort of, frontier technologies where you're taking a big bet, high risk, and you need to build that capability? Thank you.
Thank you. Yeah, so it's a great question, Leslie. So I think we're living and breathing that at the moment. So obviously, the research base in Australia is incredibly strong. If you look at the TRL scale as you go up, then obviously it starts to peter out as you get to the point where you will start to have commercial products here. I think in general, we've got growing venture capital that's coming to Australia, but we don't have those kind of deep tech investors that look at the long-term play. And so at the moment, we've been fortunate with the Research Council Centre of Excellence scheme. Obviously, the government got behind and funded our company 5 years ago, so that's been critical. Going forwards, I think Australia generally needs to get more deep tech investors involved. But also I do think with defence, having them involved in these long-term strategic areas, I understand that there are a lot of critical issues that defence has, but some of the funding that they could give to these areas where Australia has demonstrated leadership could really help us across that kind of valley of death to commercialisation. And that's really, I guess, the key challenge that a lot of us are facing. And so now in the quantum computing space in Australia, there are lots of startups that are coming out, lots of SMEs. Like I said before, I guess the critical part to look at that is the long-term economic benefit will come from controlling the hardware, not letting that go overseas. Once that's gone, then all the software and everything else, the majority of the economic benefit goes. Given that the huge strategic importance of quantum computing and the spillover benefits that come from all the other industries that are going to benefit from having that here, that will help anchor the supply chain and the ecosystem that you need. So once you've got the hardware there, the software teams and all the control layers will go towards where the hardware players is, because that's where they need to sell into. And that is what creates the ecosystem. And that's very telling. If you go back to the Silicon Valleys at the beginning, it was the hardware teams that nucleated Silicon Valley, and it was the hardware teams that then, at that time when they were making chips, they were putting them in transistor radios. They had no idea, that we would have GPS or guided missile systems, that we would be able to communicate across the globe. And so quantum computing is at that stage now where we have the opportunity to anchor hardware here in Australia, build the ecosystems around the hardware, and then 30, 40 years' time, there will be whole new industries that Australia has nucleated because of that.
So, Michelle, do I understand that one of the features of this industry, if that's the right thing to call it, is it's basically it's capital intensive to get that hardware, right? I'm just wondering what the SME environment looks like in Australia, where so often the problem is access to capital, right? How does that place the kind of expertise and industry smarts that you might see in that SME environment?
Yeah, look, so I think one of the other things that people get very nervous about is that capital intensive.
Yes.
And I guess if you were starting from scratch, as some countries are, literally, have only come in the last few years, then they've got to build up, the $100 million facilities to start with. I guess Australia is in that position because of the Centres of Excellence. It has set up those facilities already. So a lot of the capital has been spent on building up the infrastructure. We heard about the CHIPS Act earlier. Obviously in the US with the semiconductor foundries, those are multi-billion-dollar large-scale systems that the US is now investing in. And it would be kind of crazy for Australia to think about getting those in the short term because they are so expensive and they need basically skilled personnel. But some of the facilities we have in the quantum computing space don't need those billion-dollar foundries. We don't need them. So we can build everything and manufacture in-house with facilities that have cost us to date $150 million. And so again, we've got to think about not what everybody else has and what we would like to have, but what we have and build around where we have strengths. And then with those SMEs, if you find, as we are finding, we're getting people that come from 5G technology in to run our quantum chips, and they're building hardware that they themselves can sell to other companies. And so you just start to nucleate, putting SMEs working together in the Australian ecosystem without going for these enormous manufacturing plants. We don't need those. Then you can actually scale quite nicely with the system that Australia has. And obviously, the more venture capital we have and the longer deep tech players we have in the venture capital space, the better.
Another question, please, for Michelle. Yes. Microphone is coming your way.
Paul Wiley from University of New South Wales. Thank you very much. Is that on? Yes. Fascinating talk, and great to hear from a steeped practitioner. The question I'd like to put to you has to do with who should bear the risk and the management of good waste, or good risk and bad risk, and the waste that goes in an experimental type of context, and what is the role of government in that sort of process at this stage of our systems development. It does seem to me that if you look back at some of the historical innovations, the government, particularly in the military technology area, for better or for worse, was a prime mover in funding some of these sorts of things. In some cases it got out of the way, in other cases it didn't. What role do you see for government in your enterprise at this stage of its development?
That's a great question. I think, again, I just highlight, so the government's clearly played a big role in the research system and then investing in the company. But if you look at, in quantum computing in particular, if you look at the investment that's going globally, 90% of the investment in quantum computing is coming from government. It's a long-term deep tech play. It's a whole new industry that's coming. So at this point, for me, I think government has to invest where it has global leadership. It's very simple. I don't think any government can invest in every platform technology in the quantum space because there's too many, and it's, to be a leader, you have to focus your efforts and concentrate around those technical skill sets. So for me, really, it's very easy to look at where people lead, and government should get behind them and push them across that point until venture capital picks them up. That would be my view at the moment. Otherwise, if you think about it, all that investment we've had today is lost. So, the strategic long-term benefit for the country, the economic spillovers that are going to come from that technology, with the global leadership. I think that's where government should get behind. And I think that's true of several areas across Australia, not just in quantum computing, obviously.
Just to sort of follow that up, though, Michelle, I mean, my experience of government is that it doesn't engage with risk very well. And indeed, most of what government does is about managing away as much risk as it possibly can, which may or may not have a bearing on why it takes us as long as it takes us to actually bring on new elements of defence capability into the ADF. Whereas in the US, you have DARPA, you have IARPA, you've got areas that have been deliberately, created deliberately to enable people to experiment with crazy ideas, fail in some cases, but then have unbelievable successes in others. In Australia, we just don't seem to be able to do that.
Look, I definitely see that Australia is risk averse, but I guess given the strategic changes across the world, we're at a point where I don't think we can be content anymore to carry on with what we've done in the past. So I was obviously very taken with the sense of speed the US representative talked about before. Things are changing globally rapidly. I think Australia, for a long time, has invested in its research base, is seen as a talent pool for the rest of the world. But it's about time we owned what we make here. It's a sense of national pride, but it's also a sense of the long-term security. And we have something of high value to share with our AUKUS partners. So we should be making the best of it.
Okay. We've got time for one more question, and please, over here.
Is this on? Yep. Paul Fraser from UNSW Canberra. This is a question I've wanted to ask you actually since I watched your Australian of the Year acceptance speech, which was incredibly inspirational. And being a nuclear physicist, now's the time for me to voice a grumble that most academics have. So when I started my PhD in nuclear physics 20 years ago, I was told it's deader than dead in Australia. Don't get into it, you're wasting your life. Now is the moment to shine. We now are looking to do this research for the state, but when we go to seek funding from the state, it's about 15% success rate from the Australian Research Council. I was just wondering, with your access to the halls of power, what have you been able to do to advocate for funding broadly in research?
Yeah, look, so I think, that year as Australian of the Year, I very much focused actually on getting people into science because we had a pipeline issue. But I'm also, hugely passionate about the fact that, we take taxpayers' money to do the research in the first place. We are world leaders in so many fields, but yet we don't translate for economic benefit. And so I've spent a huge amount of time on different committees, one, telling people how good Australia is and how we have that leadership role, but also trying to create those schemes that get us across that valley of death. So it's, for me, I guess it's kind of funny not being born here. I have this tremendous responsibility to give everything back I can because I believe in what happens in Australia. I came here because of that sense of freedom and the ability to do things in an ambitious way that I wouldn't have been able to do elsewhere. And so I will always be pursuing whatever I can within the halls of government to get them to back their research and to bring it out from the universities. So government, industry, universities working together to get the maximum benefit for Australia.
Michelle, I've got just one last question, and it really does go to what one of our strategic competitors is doing, and that's obviously I think you said $700 billion investment which the PRC is making into quantum. What's your assessment of, let's call it quantum with Chinese characteristics? Will China succeed through a kind of a volume play, or are there limits to what can be achieved precisely because of the nature of the political system, which kind of imposes itself now on the research sector in the country?
Gosh, I don't think that at all. I think I think they've been incredibly smart by sending people all over the world and bringing them back. By putting everybody in one institution, they've got a different model that is very appealing to the young people there who want to go and work with the best of the best. So I think it's a very smart and clever move. I don't underestimate them at all. I think they will start to lead.
Give us a run for our money.
Well, it's not even giving us a run for money. I think we've been too complacent for too long in the West in general, thinking that we've got leadership in these different areas. But leadership comes about from hard work and being hungry and moving fast. And so right now, I'm very much in the view that we need to be moving faster, working harder and working together. And I think it's absolutely imperative that we do. It's just, we can't afford to underestimate what's happening.
I think that's the perfect note to finish on. Michelle, it's been a fascinating conversation. Thank you so much for taking the time to come and explain the world of quantum to us, and I think I can say everyone here wishes you well in your further endeavours. And so, ladies and gentlemen, please thank Professor Michelle Simmons.